Hey guys, welcome back for day 14, Electron Configuration 2. Where we're going to look at some of the anomalies of the electron configuration where atoms aren't actually observed doing the predicted behavior. Alright, so Hund's rule causes an occasional anomaly, alright? Because what happens is these d orbitals don't always act like we expect them to act. Sometimes they act a little differently than we expect them to act. Alright. And so we're going to look at, now we have the periodic table here, and we're going to look at some of these transition metals and some of the lanthanides and actinides. Group 1 and Group 2, and then in 13 through 18, all behave normally. There's no anomalies there. It's the transition metals and then the F block down here that really can do funny things. So let's look at this. Copper. If we look at copper, we go right to copper, the periodic table here. Copper's right here. And so we would use argon as my noble gas. It's in the period above, right? So argon, and then it's 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we look at this, we would expect let's use the whole thing. Argon, 4s2, 3d9. Now, that's not what we actually expect. Okay? Because we have 4s2 and 3d. And 4s2 has up, down, and 3d 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, what happens here is that there's a spot in a lower energy level. Even though it doesn't fill first, it's still a lower energy level. And so what happens is a lot of times one of these electrons here, it doesn't matter which one, we usually use the one down, will move down there. So we actually get argon 4s1 3d10. 4s1 3d10. That's what we usually get. All right. Okay, just because it's more stable. It's obviously more stable. All right. Analogy: this again, human behavior. We make decisions. The electrons aren't making decisions as far as we know. If you've ever been to a big football game, big basketball game like Division I or pros or something like that, big stadium. Well, sometimes I would usually go, not to be in the upper level, so to speak, or higher up if it's a bowl. And, to go to the lower level, there's always somebody there checking tickets, especially at the beginning of the game. And it does two purposes. One, it does help you find your seats if you make sure you're in the right spot. And two, it makes sure that you're not going where you're not supposed to go. Well, if the game gets kind of lopsided, which sometimes the earlier season games would, those guys taking tickets sometimes disappear, and so do sometimes the fans. So in the second half, a lot of times or whatnot, you can go and you can go sit anywhere you want, as long as there's nobody there. Nobody's going to say anything to you anymore. So there's many times where we would do that, where we would go and sit down and sit lower and see. Kind of fun. So that's human behavior. Electrons aren't humans, but they go down to the lower energy level because it's more stable. So silver, what do we think happens with silver? We would expect silver, all right below here, use krypton and 5s2 49. All right, so we expect krypton 5. That's a 5. That's horrible 5. Let's go 5s2 4d9. But as you can probably guess, we get krypton 5s1 4d10. Gold. Gold. So if we look at gold, we expect, right? Well, let's go to the table. There's gold. We expect xenon 6s, right? Now, with the xenon 6s2, make sure you throw in the 4f14s 5d9. That's what we expect. Right? But we can't forget the 4f14. Right? Now, some people do all the time. But technically speaking, it's not core because it doesn't fill with xenon, right? It's not in xenon's configuration. Now, is it in gold's reactivity? No, but it's still, we still need to point out that we know that at this point. All right, what we get for gold would be xenon 6s1 4f14 5d10. Now, if you want to rearrange that to xenon 4f14 5d10 6s1, that's fine too. I'm okay with that. Now we go to chromium. Chromium. We expect for chromium, right? We expect argon 4s2 3d4, right? 4s2, chromium's right here. 4s1 2 3d1 2 3 4. But it says half or completely filled degenerate sets are stable. Degenerate means they're the same energy level. So if we go to argon 4s1 3d5, everything is half full. And that kind of makes sense. Ruthenium. All right, well, where is ruthenium at? Let's look. Ruthenium is right here. And so we're using krypton 5s. So we expect krypton 5s2 4d. And if we count, let's count. 1 2 3 4 5 6. Well, what's happening here? Because I could take one d7, d8, but not like I don't understand. Well, let's go to the side here. Look at our d orbitals. All right, so the d orbitals are 5 of them. 1, 2, 3, 4, 5. Right? We have dxy, dyz, dxz, dx squared minus y squared, and dz squared. Those are the 5 d orbitals, right? Do you need to know their letters? Probably not. But there's 5 d orbitals, and they're all the same. All right? So you would think that they're all the same energy. But what happens is that's not the case. So they start off all the same energy. There's 3 splittings of them. Right? So all the same energy. So if I drew energy here, they split into different sizes or different energies. So one of the most common ones, right, is we'll learn it's octahedral. Now we'll know the shape octahedral later on once we get to the Lewis structures, but the splitting you don't need to know. But there's 3 d orbitals that go lower in energy and 2 that go higher in energy. And the split, to be honest with you, is known, right? And delta OH they call it for octahedral. All right. But what happens is the dxy, dxz, and dyz are all down there. All right. And dx squared minus y squared up top, and dz squared are up here. I actually wanted to write those below. I'm sorry. Dx squared minus y squared, dz squared. All right. That's one. There's also tetrahedral. All right. Where this is kind of flipped. You have and I don't know, I don't remember if it's the exact same energy splitting. Forgive me. Right, where it's exactly split. You have dx squared minus y squared, dz squared down there, dxy, dxz, dyz. All right, and then last but not least, we'll have square planar. And these shapes, we'll learn all these shapes. Don't worry about the shapes. Don't worry, but the energies we'll get to. Don't stress about that. But anyway, you have up here, you'll have dx squared minus y squared. Then you have about, I think it's here, dxy. And then you have dz squared, d I want to say it's xz. You have to forgive me. I don't know if I gotta look that up again. And then d yz maybe. Don't quote me on these down here. I have to look them up. So yes, this is right. This is right. Okay. So let's look at the, if I draw electrons now, how can we get electrons in here? So I can go D1, D2, D3, and now I have a half-fill set of orbitals. All right. So I can have D3 and that actually be half-filled. All right. They're not deleting. All right. Let's try that again. So now I can have 1, 2, 3, 4, 5, 6. I can have D6 and it's half filled. We can have it as D1, 2, 3, 4, 5, 6, 7, 8. That didn't work for me. 1, 2, 3, 4, 5, 6, 7, 8. So now I have D8 and it works. Alright, so D8 could actually work. I could have D1, 2, 3, 4. Right, I can have D up to D4 there. Alright, I can also have D1, 2, 3, 4, 5, 6, 7. D7 works. Alright, I can have D1, 2, 3, 4, 5, 6, 7, 8. I can even have D9. With one up there, everybody else full. So I can have all these options depending on how the d orbitals split. Now your book doesn't go into why the d orbitals split in crystal field theory. You can look it up, but there's no, unless if this is going to be your only Chem 1 class, don't stress. If you are very interested in chemistry, crystal field theory would be something you would look into. All right, later on. So what actually happens with ruthenium? Kind of fun. It goes still krypton because that doesn't change, right? It goes 5s1 4d7. Palladium. So palladium, krypton, which is not an R, it's Kr. 5s2 4d8. Well, this one makes a lot of sense because it goes to krypton 5s0 4d10. That makes a lot of sense. Platinum, right below it, xenon. Then we got 6s2. Of course, the 4f14 is in there now. And 5d8. So you would think that this would go to xenon, right? 6s0, but it goes 6s1, 4f14. 5d9 because platinum likes to be square planar a lot of times. Alright, niobium or niobium, excuse me. We expect it to be krypton. It's 5s2 4d3. So you would expect alright, d5, button weight. Krypton 5s1 4d4, right? And last but not least, molybdenum. All right, we expect molybdenum to be krypton 5s2, 4d4. And this one we do get what we expect, where it is krypton 5s1, 4d5. So how am I going to know that? Right? That seems like a lot to know. Kind of weird. So on the next sheet of your handout, you have this. And it shows you all of the elements and their endings, right? So if you notice, group 1's all S1, group 2's all S2, D1, then you got some D2s, you got D3, D4, D3, right? And so you got all these, but then you got P1, P2, P3, P4, P5, P6, except for S2, right? So this tells us. Now the ones that steal that we need to know, all right? Obviously, copper, silver, and gold. Those are blatantly obvious, right? They're the same. Those are the three, and I hate to use cliches like gold standard, but those are the ones that steal first. Now, palladium is one that works too, where all the S's go to full D. Chromium and molybdenum are also good ones that make sense. All right? They make sense. Okay, there's some that don't make sense. Well, it doesn't make sense. Rhodium. All right, rhodium doesn't necessarily make sense. Ruthenium doesn't necessarily make sense. Okay, niobium doesn't make sense. So it's 3, 4, 5, 6, 7, 8, 9. And platinum. All right. So those are ones that don't make sense. Now, if you look at the F blocks, if you look, everything with D1 is good. So that one, 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 that one. Almost looks like most of them are the exceptions, right? So there's more exceptions than rules. So that's why, right, don't memorize those. All right, the green ones make sense in terms of things. But again, electron configuration, you're going to be able to look this up. Okay? All right, you're going to be able to look this up. This is not like a huge thing, but it's good to know that some of them steal, why they steal, because it's stable, lower energy level. All right? Okay, now there's one thing I just skipped over here, which is unpaired electrons. And unpaired electrons rise to magnetism, and that goes on later on to important things. Sodium, how many unpaired electrons does sodium have? All right, that's a good question. Well, okay, now all core electrons are paired. So all core electrons are paired. So sodium is S1, it has 1 unpaired electrons. Yttrium, D1, would have 1 unpaired electron. So you might have to actually draw the boxes like we did before in day 13 and look at the boxes, the orbital diagram to do this. Potassium has 1 unpaired electron, S1. S2, 0. Scandium would have 1. Titanium would have 2. Vanadium would have 3, D3. Chromium, now chromium, all right, is S1, 4S1, 3D5, so it actually has 6. Manganese has 5. Now these two are special, and I'm just giving them to you. You will never be asked this on a test. 4 and 3. 4, 3. Palladium, D10, 0. Silver, 1. Cadmium, 0. The ones that kind of make sense that maybe would ever show up, indium would have P1, P2, P3, P4, P5, and P6. That makes sense because as the p orbitals go, 1, 2, 3, 2, 1, 0. All right, but those are the unpaired electrons. Don't stress about that too much. It comes more later on if you take another chemistry course. right? And again, this periodic table, helpful, very helpful, all right, for electron configuration. Now, the one thing we did not talk about yet is ions. We alluded to it, but let's talk about ions real quick. So we can either gain or lose. So if I have oxygen, I'll use oxygen for an example. That's a Q. Let's go with OXYGEN, right? So O versus O2 minus. So we have 8 electrons versus 10 electrons. So oxygen, now, I'll be honest, 1s2 versus He. Which one's the shortcut? I don't care which one you use. If I'm writing by hand, 1s2 is faster for me to write. If I'm typing, helium is faster for me to write. So it just depends on what you want to do. So 1s2, 2s2, 2p4. Or, right, what's going to happen is we're going to add the electrons. So they're going to go to the p orbital. So we're going to get 1s2, 2s2, 2p6. And it's isoelectronic with helium, right? Alright, not helium, with neon. Okay, and that's why oxygen likes to be -2, right? So we call it isoelectronic. It's the electronics configuration of electrons is the same as neon. Alright. So gaining, you just keep going. It's pretty easy to gain. Losing's different. Iron, so I have Fe versus Fe2 plus versus Fe3 plus. Alright. So iron, electron configuration, I would use the noble gas of argon. And then it's 4s2, 3d6. Well, if I lose 2 electrons, what is lost first? So if we put it in the stripping order, argon, 3d6, 4s2, right? So argon, I'm sorry, iron 2 plus will be argon, 4s0. You don't have to write that. I'm just writing it down. 4s0, 3d6. Right, because I take the S apart first. Iron 3 plus, argon. Right, it's still 4s0, but it's 3d5 now. Right, so I take the S first, then the D. Right, so the order that we come off. Right, P, then S, then D, then F. So that's the stripping order. Right, P, then S, then D, then F. So that's why some, put your noble gas, and then you have F, D, S, P. A lot of times they'll do that. All right. So that's the stripping order. That's ions, and that's all. That's all the electron configuration. All the electron configuration we need to do. So again, you can look them up. Ions, you add for negative, you take away for positive, and that's how you take away. So hopefully that makes sense, and we'll catch you guys next time.